Hello and welcome to an edition of the GOTO Book Club. My name is Matt Godbolt, and today I will be interviewing Dan Kusswurm. And well, first of all, I should say a little bit about myself. I know every episode of this has a different host, so I am mostly known for a website called Compiler Explorer, which allows you to type in C and C++ code and other compiled languages and see the assembly output. And so I've spent my entire career dealing with assembly language. And when I got an email to tell me, or rather invite me to do this talk, I was delighted because this is one of the few books that I actually own. So Modern X86 Assembly by Dan Kusswurm is in fact one of the few books that lives on my desk. And so it's a fantastic opportunity for me to be able to talk to the person who wrote it. And I realized I don't know very much about you, Dan. So why don't you give us a few lines about yourself and introduce yourself?
Okay. Well, firstly, my name is Dan Kusswurm. I'm a software developer, computer scientist, author. I spent the bulk of my career developing software primarily for embedded systems, scientific instruments, medical devices. Most of the code that I've written throughout my career has been in C++, with the occasional where it's justified in assembly language. Also dabbled a little bit, which everybody seems to do these days, in some Java, some Python, Rust, and stuff like that. You kind of wrestle with anyway. But again, my primary background has been computational software in medical devices, a lot of image analysis type work. So the things where the potential use of assembly language is potentially viable.
Right. So I suppose we should really starting by talking about what is assembly language and why should I care about it?
Well, assembly language is the low-level language of the processor. It's basically the native instruction set of the processor. And if you look at different processor families that are out there today, you have your X86 family, your ARM families and stuff like that. There are different assembly languages for those. And in fact, within those processor families, specific processors also support various different instruction sets. And basically what an assembler does is it takes those instructions and translate it into executable machine code that you actually run the processor. Now, if you look at it from a higher level language, if you look at it like from a C or C++, basically,
I love that C is a high level language in this world.
yeah. So basically, your compiler, in essence, is translating your C or C++ code, or even your Rust code, into assembly language, and an assembler then takes that and converts it into executable machine code.
Right. So I think this is something that I see people use interchangeably, machine code and assembly code or assembly language. So What is the distinction between those two things?
The distinction there is that assembly language is the actual source code. It's the mnemonics that actually define the instructions. The machine code is the ones and the zeros that actually get executed on the machine. So that's sort of the differentiation there.
Right. And then presumably there's the assembler is what takes the assembly code and turns it into this machine code.
Yeah.
And but what's different from that from, say, a compiler? I mean, like a compiler takes my code and generates assembly code kind of, or?
Yeah, a compiler is actually doing both. A compiler is actually translating, depending on the compiler course, it can translate it into assembly language code, and an assembler can come along and translate it into machine code, or the compiler may do a direct translation into machine code.
Right, I see. But at this level, an assembler is taking something, but it's for a specific CPU architecture, maybe even a specific model of that CPU.
Exactly, right.
Whereas usually a high-level language is phrased in a way that's, in theory at least, more platform agnostic.
Yes, that's correct, yes.
So if the compiler generates assembly, why do I even need to know that it exists?
That's a good question. I think let me back up a second here. Let me talk about sort of where the motivation for the book began, because I think
that's a great
help answer your question there. Back in the 2012, 2013 timeframe, I was working on a project that involved some hemi image analysis. We were imaging slides, microscope slides that had cells stained on them there. Okay. And you'd have a slide that could potentially have 100,000 cells on it. Okay. And this is pre-AI days. So it's a lot of old school image analysis. Okay. A lot of heavy duty number crunching there. And I was kind of looking for a way to sort of improve the performance of our software product. And I've had some experience with X86 assembly language going back to my early days as an undergrad. But I didn't have too much experience with the SIMD extensions, the SSEs and the AVXs and stuff like that. So what I decided to do is I took a close look at where sort of the performance bottlenecks were. and identified those functions. And I decided let's write some SIMD code to sort of see how if I can improve the performance of these image processing functions. And it wasn't like massive amounts of code here. I mean, the core base of the code is still in C++, but we had, there's maybe, at least initially, there's maybe 10 or 12 functions that let's try to make a SIMD algorithm of those to see if we can improve performance. And back then, compilers weren't very good at generating SIMD code. So what I did was I got out the Intel manuals and learned all the SIMD instructions. It was SSE back then. And, the manuals are good for telling you how each individual instruction works, but they aren't very good at telling you how to put together complete algorithms.
Of course.
So that was sort of the motivation for them.
They're a reference of what they do rather than like hey, here's how to use it. So I'm going to pause there because I don't know if it's necessarily obvious what SIMD is and what these various other things you've just described. So do you want to talk a little bit about what SIMD is and what makes it sort of different from normal?
Yeah, SIMD is an acronym. It stands for single instruction, multiple data. And basically what it is, normally on a computer, if you're, let's say, doing a simple addition or something like that, a simple addition of two arrays, let's say, for example, it'll add each element of the array one at a time there. Now, what SIMD does is it takes maybe chunks of data, maybe 8 or 16 elements at a time, and performs the same arithmetic operation on those elements with one instruction. So if you think about it, instead of doing 16 separate adds or multiplies or whatever, you're now just doing one arithmetic operation and getting 16 results.
Got it. And do these 16 need to be, can I just pull them from anywhere, or how do they, what's the relationship between these 16 things?
You can pull from it, but generally you're normally doing like with matrix and vector type operations.
So you've got a massive array of these things and you can pick up a chunk of them.
You get a massive array of data or a massive array of matrix elements there. So like for high performance computing applications, you're dealing with large arrays, you're doing large arrays of cross products or vector products or that type of stuff there. Matrix operations or matrix vector operations.
Got it. And so SIMD allows me to write one instruction, so a multiply or an add or a subtract or whatever it is, and it applies to 8 or 16 things independently. Are they sort of packed together in some way, or how does that work?
They're packed together as a vector. Okay. So if you look at it from the internal architecture, you have a register inside the processor that can hold these 8 or 16 values at one time.
Got it.
Okay. And if you look at the book, there's some diagrams in the book that actually illustrate how SIMD operations actually work.
I'm trying to find them now. Of course, now I've got it open. I can see some of the parallel word instructions here, but those are the ones that my book just opens at. So, but yes, there are some great diagrams in the book explaining this concept of like how you can interpret this ultra wide register as different sized slices of things.
Exactly. Think of a normal register on a processor, maybe 32 bits or 64 bits. SIMD registers are typically a minimum of 128 bits, and they can go to 256 or 512, at least on the Intel architectures.
Right. And then that 512 bits could be 256 shorts or, no, it's 256. My math is terrible, but you know what I mean? You could see it as a number of...
It could be 16 single precision floating points or 8 double precision floating points or 64 one-byte integers if you're doing some integer arithmetic.
So, I mean, just out of curiosity, why is that? Why not just make the processor faster? It just seems like you're making me do a ton of work that it could infer, surely, or some cleverness here, right? Why can't the CPU just be quicker? Why is it better to do this sort of bulk operation?
Well, what you're doing here is this, instead of doing one bulk operation on wide registers, you'd have to do 16 or 32 or whatever it is, individual operations. And usually you would have to set up a small for loop to actually do that. So that takes time.
Right.
So for a SIMD operation, they're again, for the right types of applications, they're generally much, much faster than sort of scalar arithmetic.
Well, that obviously it makes sense if you can do 16 at a time. So presumably the chips are physically capable of doing these things simultaneously 16 times, and that sort of blows my mind that you're talking about like potentially multiplying 8 double precision numbers together at once in one instruction.
Yes,
But that
absolutely.
is what's going on, right? There's not like inside the chip, it's looping over them or anything like that.
No. It's actually one instruction. So again, it's one instruction, does the 8 or 16 or whatever it is, arithmetic operations at once, as opposed to doing individual scalar operations.
Right. That makes sense. So yeah, you were telling the story, and I can't remember if I'd cut you off halfway through. So please carry on.
Yeah, so then the motivation for the book was to use the SIMD extensions on the X86 platform to improve the performance of these image analysis algorithms. And like I said, the reference manuals are good for teaching you how to use individual instructions, but they don't really elucidate, complete algorithms. And that was the focus of the book here. I wanted to write first of all, I couldn't find existing books that covered SIMD algorithms in any sort of sufficient or at least adequate detail. Some of them back then, were superficially covered, SSE and AVX, but there was no real in-depth book that I found satisfactory. So I figured, well, wait a second, I'm doing a lot of trial and error here myself. Maybe other people can benefit from my expertise, my experience, my learning curve. And that was sort of the motivation for the original book. Now, the problem is, not really the problem, but the challenge is you just can't go and learn SIMD instructions for a particular processor architecture. You got to learn how to create for loops. You got to learn how to do basic integer and floating point arithmetic.
Right. There's
how to do compare.
A lot of bits around that you find yourself writing if you need to do the scaffolding.
Memory addressing modes.
Oh, gosh.
It's not just simply going and learning a few SIMD instructions and writing some quick code. There's a lot of sort of background you need to know, register architectures and stuff like that. So if you look at the book, the first, maybe a third of the book covers basic x86 architecture, and the second 2/3 of the book focuses mostly on the SIMD instruction extensions, the AVX, AVX2, and AVX512.
Got it. But sort of the intention behind this was to be a crib sheet for people who want to write SIMD-based algorithms, and we'll talk about some of the challenges about that in a second. But in order to get there, you kind of have to get over the whole of the ISA, and this is specifically for x86. Although I know that you've also done similar books for other processors.
Yeah. The book that you're holding is strictly an x86 book. There's also an ARM book that I did a couple of years ago, back in 2020.
Got it.
And basically similar types of topics, but again focuses on the ARM platform as opposed to the x86 platform.
My understanding is some of the concepts of SIMD are broadly the same across architectures, but it's the devil is in the details as about how each CPU does it slightly differently, right?
Yeah, there's different instructions, and there's some slightly difference in the specifics of the architecture, but the basic principles are exactly the same.
Got it. And now I've got the first edition here, and then I was looking through my ebook reader version of the latest version, and so which is it the third edition? Am I right?
Yeah, the third edition is out now. Yeah,
and I see that you've finally dropped the old x87 ancient prehistoric floating point version that nobody has used in a very, very long time. So that was a welcome thing when I was sort of reading through the updates here. But yeah, so your intention was to write a SIMD book, and then you ended up writing a pretty comprehensive assembly language programming book that tells you pretty much everything about how to program. Tell me about what makes SIMD algorithms challenging then, because surely you just if it was easy, the compiler would do it for you, which I'm sure we'll talk about in a second.
Yeah, there's a couple of reasons. First of all, compilers are getting better in automatically generating SIMD code. I mean, they've improved quite a bit, especially since I wrote the first version. There's a couple of challenges when you're writing SIMD code. I think first challenge, if you're developing an algorithm that has a lot of decision making in it, if then else, that type of stuff there, compilers still have a little bit of difficulty generating that by themselves.
Well, so yeah, can we pause there actually? Because that now you've explained how SIMD works. You're talking about picking up 16 elements at a time or whatever. Mm-hmm. Obviously, you're having to do, if it's a single instruction, multiple data. We're doing the same thing to 16 things, which means that what if I only want to do it to some of these things? Or what if I have a branch? Or what if it's once I reach the end, how does that work?
Well, that's one of the programming or the sort of the programming differences between sort of normal programming and SIMD programming. On SIMD programming, you make your logic decisions not by saying if X is greater than Y, for example, do this, otherwise do that. You have to say if X is greater than Y, you'll get a mask that tells you whether that's true, that statement is true or false. And through some simple Boolean operations, you then can throw away the data that you don't need and then keep the data that you want to need.
I see. So sort of like a ternary operator thing, but presumably I have to evaluate both sides of what if I want to say, if, clamp, I presume there's a clamp primitive, less than 0, whatever. But like if I wanted to say, set it to value X if it's less than X, otherwise leave it alone. I kind of need to have done the work for both forks of that and then select which one somehow.
Yeah, yes and no. Let's say, for example, again, going back to the sort of simple example of I'm concerned about X greater than Y or something like that. Okay. I'll get a mask saying whether it's true or false. So I obviously know whether it's true. And if I just do a not on that, I have the opposite condition right away.
Right. But if for example, it was like, if I wanted to do, if X is less than what, element by element in a 16, so presumably X is 16 elements wide, Y is 16 element wide. I'm doing element by element comparisons. And then I want to sort of say like, if X is less than Y, then I want the square root of X. Otherwise I want the cube of X, right? At that point, I have to have done both sides of that. So there's presumably a point where you go, actually, your logic is too complicated, time out. If you should use an if statement here, or where do you make these sort of calls about that kind of thing? If that makes sense to you, if what I've just described.
Well, again, going back, let's say, I got 16 X's and 16 Y's, for example. I do whatever initial comparison I do. I've now got 16 results in one of these wide registers. Mm-hmm. Okay. So now I can, and again, take for the example, I'm interested in doing the trues. I can do the trues. I can take my square root, for example, and then the falses, for example, I can do the cubes. What I also can do is I can take those 16 results and compress them into a single bit mask that I can move to the processor and test those, what's the right word for it? I can test those, but there's also on the X86 architecture, there's instructions that allow conditional operations, for example. Oh. And this is where AVX 512 kind of shines in that I can do masking operations on the instructions. So I can say, okay, only update the registers that were the condition was true, and then take the positive, the opposite case, update the registers, doing a different arithmetic operation where the condition was false.
Got it. And then presumably with this mask register as well, you could add in something which says like, if they're all false, then I don't even have to do the true branch of that kind of stuff. Right. So you can do some amount of conditional stuff, but it's like, it starts to blur when it's valuable to do this. Because if one of those paths is hugely expensive and rare, then maybe it's not worth vectorizing, but then maybe you think about your algorithm in a different way. And is this kind of what you're talking about?
I think the latter is probably more important. You think about the algorithm in a different way then. Yes, absolutely.
Right. And so that is probably the bit where compilers fall down because they don't know what your algorithm is. They're trying to infer something from the way that you wrote code, and they're limited in how much they can rewrite your algorithm.
Yeah, again, to take a very simple example where I'm just adding 2 arrays and storing into a third array. That's, compilers can pick that up these days and generate some really efficient SIMD code for doing that. But again, where there's logic decisions involved, they have a little bit more difficulty in doing that. I guess the other case where compilers still lack efficiency is taking advantage of instructions that are sort of that target specific applications. And to give you an example, the X86 SIMD architectures, the AVX architectures, they have instructions for manipulating sparse matrices. Okay. Oh. That's a very targeted specific application. And a compiler has, difficulty generating that. And I'm not sure you'd want a compiler to generate that because that's a really targeted application.
It's a very specific use case.
Exactly.
Right. And so, you don't, given all the heuristics a poor compiler has to go through to say, maybe they were trying to do this, maybe they're trying to do that. At some point, there's a law of diminishing returns. It's like, they're probably not doing motion compensation for MJPEG here.
Exactly.
You probably shouldn't be looking to use that instruction here. Right. I get you. Yeah. And things like carryless multiplies and things that you can do and some really obscure things that you shouldn't. But from my own experience, I found that there's often an intrinsic that I can use in my C code. So where's the kind of like line to draw where I can write these sort of guided, not really portable C++ anymore and get the code that I want versus when would I crack out the assembly book and just go, no, I'm just going to write this.
Well, I use intrinsics myself. They're very useful and they're good for doing a quick assessment. Let's say I'm not really sure how much performance I can gain by doing a full-blown assembly language, coding. I might try intrinsics first, get a sort of a rough feel what the performance gains are. And if it looks like I can maybe squeeze some more out, then I'll go do some assembly language. the one thing I do like about going to the sort of the pure assembly language approach when it's warranted is that you get to take advantage of stuff that's within the assembler, things like macro processors and stuff like that. The full access to the full instruction set. Okay. Whereas you don't have that with Intrinsics. You got quite a bit of access with the Intrinsics, but not the full instruction set. Or, for example, if you're doing some hardware manipulation where Intrinsics really don't help you with that, like maybe like a device driver or something like that, or doing code for an embedded system, Intrinsics don't really help you in that case. And again, in those situations, assembly language is justified.
That makes sense to me. I mean, I can see that there's a law of diminishing returns. I mean, and also there's a point at which, from my own experience, when you're writing intrinsics, and just for those who don't know what intrinsics are like, they look like function calls that you're making in C or C++, but the compiler knows, nudge, nudge, wink, wink, that actually you should generate a particular instruction here. But at some point you realize that you're just writing assembly with a worse syntax in C, and you might as well just crack out.
That's a real good observation. To use the intrinsics, you have to understand what the underlying assembly language instructions does. Okay, there's just no way around that. So you're kind of 80% there already to doing, assembly language code. So, you take the next step and do the actual assembly language itself then. So, but you do have a choice there.
But I mean, if you are writing assembly, you have to, you suddenly are beholden to some of the other architectural details, which again is what part of this book is about, right? To get you to that point. So things like, what register should I expect parameters to be passed in? What registers must I preserve and pop and things like that? So there's a lot more like glue that you need to write yourself if you're just going to drop into and write a function that you can call.
Absolutely. There's what are called calling conventions, and as you alluded to, certain arguments are passed through registers, and depending on the number of arguments a function has, you may have to pass arguments on the stack. You have what are called different processor registers are called volatile or non-volatile. A volatile register doesn't need to be saved by the called function, but a non-volatile register does. And again, depending on the architecture and depending on the whether you're like doing Windows or Linux or something like that, there are different register usages and different usages of how the stack is organized. And again, this is something that the book the third edition especially dives into a lot of the differences between, let's say, both Windows and Linux.
Right. And things like,
and how to do that.
As you say, stack red zones and things like that I like. I don't have to think about most of the time because the compiler does that bit for me. Right. And so this is like, where you're exposed to it. But also when I was reading, that was actually the bit, because I read the bit at the beginning that was the most different. That was a bit that stuck out to me as being like, oh, this is cool. Actually, I didn't understand fully what the red zone was all about and why it's okay. And then why is it useful? Okay. Well, it just means I don't have to manipulate the stack pointer. I know, some good stuff in there.
Yeah.
So let's talk a little bit about, well, first of all, actually, what have you got some favorite examples of optimizations and things that you've done that you can look back and be like, yeah, look, we sketched it out and then we were actually able to blow the compiler's generated stuff completely out of the water.
Yeah. One of the examples, or next there's a couple, there's some real basic operations, just simple statistics, calculating the mean of an image or something like, or calculating a variance, you're doing a lot of summing, and you ultimately do a square root and get your variance, your standard deviation or whatever. So those types of operations you can get, several times improved performance. Now I'll caveat with this. If you're doing an application where, you do this one-time operation, it's not worth jumping into assembly language to do that. If you're doing real-time programming, take, for example, you've got your camera's capturing 30 or 60 frames a second, and you need to build a histogram for each one of those frames and then calculate some basic statistics, then it's worthwhile considering using assembly language. The other use case that I encountered there, doing like convolutions, either 1 or 2D convolutions. And basically a convolution it's just an arithmetic operation on an array or matrix. Mm-hmm. Like, for example, if you want to blur an image, you might apply like a low pass filter. So now you've got your actual image and you've got a small little operator. It's called a kernel, and you blend the two together and you get your result. Well, SIMD operations and assembly language programming in particular are really good for those types of operations. If you're doing some unusual convolutions, or you've got some strange masks or kernels and stuff like that, those are the types of, at least the use cases that in my mind stick out, where it was justified to jump into it. It was justified to do the assembly language programming to get the performance gains.
Got it. That makes sense to me. Yeah. I mean, it's definitely those kinds of things sort of spring to mind as being the obvious thing is you're picking up data and you're doing the same thing to it over and over again. And maybe there's a tiny sum at the end or whatever.
Exactly.
One thing we should really talk about then is like what makes assembly language more difficult to integrate into, say, a normal development flow. Yeah. Are there challenges? What do we need to think about in that kind of side of things?
Yeah. In some respects, it's the same development flow. You define what your function is going to do. You put together requirements, design documents, code your function, you test it. So that part's no different. I think the important part of that is that you always need to benchmark any assembly language code that you generate. And, the reason for that is that, if you're not getting any substantial performance gains out of it, and by substantial performance gains, I'm talking a significant, like double or triple or something like that.
Right. Okay. So that's an interesting observation there because, 10% faster sounds good to me, but you're saying that we can get 2-3 times perhaps.
Yeah. Yeah. It depends on your application too. 10% might be warranted in some cases, but in a lot of cases, it's not going to be warranted.
Right. Okay? And so what's the trade-off there? Why, if I can get a 10% speed boost in my, thing I call a couple of times, why not just write it in assembly? Why?
Well, you certainly could. It basically boils down to you're trading extra development time for performance gains and future maintainability.
Got it.
So it's kind of a balance between those three items.
That makes sense. But otherwise, the flow is relatively similar to...
The flow is, again, outside of the benchmarking component, the normal software development, life cycle or workflow is pretty much the same.
And then, benchmarking is its own black art. It's so difficult to get that well.
Benchmarking is its own topic. Now, there's a couple of ways of doing that. The crude approach is you set up a simple for loop and just, constantly call your function or test a million times and measure it. And, that gives you a rough idea of exactly. It's a rough idea. Yeah. A better approach is if you go to, either the Intel or the AMD websites, they actually have profiling tools that allow you to sort of dig deep and get a much accurate, a better representation of how your algorithm is actually performing. And I think if I recall correctly, some of the new tools, there's a new performance tool that you actually can use, to do profiling and get a much better, measurement as opposed to just, sort of simple calling the function a million times and then, calculating a mean and a standard deviation.
Right. And even those things, given how complicated processors are these days and all the tricks they pull off behind the scenes, you can easily convince yourself that something's good. And then when it's actually in the production environment, when you don't have a cache to yourself, when you don't have a pre-warned branch predictor, everything goes out the window. So you have to be a bit careful about that kind of thing. That's why
I'm just going to raise that point. Those types of benchmarking approaches don't really reflect your real world caching. So you're right. You're absolutely right.
It's difficult. From my own experience of this kind of thing, the only thing I've found that I can do is to have a CI system that graphs over time my performance in various characteristics and then kind of almost post hoc go, oh, hang on a second, we introduced something that made it go slower. What was that? And sometimes it's like somebody added a line to an innocuous place. And this is more for compiled languages. And now suddenly everything's gone out of alignment and something here. But like with assembly, I suppose you're controlling that a lot more, but you pay for that in development time because a human has to go in
development time and you potentially pay for it in future maintainability too.
That makes sense. Yeah. And maintainability is often the most limiting factor in software development lifecycle, but sometimes it's worth for the performance gains if your domain demands it or whatever. I come from the trading background. So, for high frequency trading, we don't mind spending the time and effort to do this, but for like medical imaging, as you said, great.
Yeah, you're doing real-time applications, your multimedia applications, game development, those types of things where it makes some sense to at least consider looking at your IO your computational bottlenecks, and then consider using assembly language. Obviously, if you got an IO bottleneck like a file or a network or something like that, assembly language is just not going to help you at all.
Yeah. Oh, yeah. And even cache layout, memory layout, stuff like that. That's the thing you can often attempt at a higher level language before you roll down to it. And also is perhaps a precursor to, if we can get everything in a line, then this already looks good for a vectorization later on.
Yeah. Well, that's a good point. One of the things that I found is that, by doing assembly language programming, when I go back to C or C++, I'm always, cognizant of the fact, I want these elements or these members of a structure or a class to make sure they're properly aligned on a cache line boundary, or at least a 16-byte boundary. So that's going to improve performance a little bit.
Yeah. So these things, even just being aware, I think, it's the kind of thing that if you're in a performance sensitive environment at all, understanding what's going on under the hood is always worthwhile. And one way to do that is to pick up a copy of your book and kind of like play around with some of the examples that you've got and kind of lead yourself through that process of saying, oh, this is how the computer is actually working. And then later on, you can see how these pictures map into the higher level languages you're perhaps used to writing. And then you might have an inroad into one day saying, this function could be 100 times faster or 10 times faster.
Absolutely. It's a good way to summarize it.
Fantastic. Well, I think we've probably got to the point of time here with we've got obviously tons more we could talk about. I feel like you and I could talk on for hours and hours.
Absolutely.
But is there any sort of parting words that you'd like to say? I mean, obviously everyone should go and grab a copy of this book. Well, not this book, the new version.
The third edition is out. You can, if you're interested in buying a copy, go to your favorite online bookseller. You can also go to link.springer.com. That's the publisher's website. And all the Springer publications are there. Just type in Modern X86 or type in my name, and you'll come up with a list of the books that I've published there, and you can get a copy there.
Fantastic. Well, thank you very much for talking to me today, Dan. I've really enjoyed this conversation, and I hope that we're introducing some more people to the idea that maybe they should learn assembly language, because it's something that's dear to my heart.
Yeah. Well, thank you for having me. Appreciate it, Matt.
Subscribe to the GOTO YouTube channel now and join the experts in person or online at any upcoming GOTO conference using the promo code Book Club. Visit gotopia.tech to learn more.